Alright, so welcome to these video lessons. So if you're watching this, it's because you either A, need a little bit of a refresher on what's happening, or B, due to the circumstances, had to self-isolate for a few days, or you've just been sick and you missed some class. So basically what we're going to do is go over the exact same stuff, well, the exact same lessons you would have got if you're in class, using, of course, the exact same notes that hopefully you have. If not, the blank copies are going to be provided on Google Classroom as PDFs so you can print them off and follow along. Now, also with these here, there's always going to be a workbook or a CYU, that stands for Check Your Understanding. You should make sure you have these and try these as well at the end of every section. So we're going to start with our introduction to diversity of matter with, for the most part, we're going to be looking at chemical bonding. So our theory is going to come from someone who started this whole idea about chemical bonding, a guy or a scientist named Gilbert Lewis. So he proposed first that atoms could achieve stable electron configurations by either gaining or losing electrons. And he just studied the valence electrons. So remember, valence is the ones that are in the outermost shell from your Bohr diagrams. So by studying valence electrons, we can begin to predict and understand how chemical formulas for ionic and even molecular compounds form. So just remember, whenever you see the word valence, like valence shell, valence orbital, valence energy level, in this case valence electron, these are electrons in the outer energy levels of the atom. Now, we are going to describe these energy levels now as something called an orbital. So when we did our Bohr models, we are going to look at these a little later. We referred to them as orbitals. We referred to them as energy levels. Now we're going to start referring to them as orbital, and that's technically the correct definition. So all an orbital is, it's just a region of space where an electron may exist, right? That's its energy level. So when these rules aren't going to change, the first energy level, or our first orbital, is only going to contain one orbital. So the first energy level contains one orbital, and each orbital can only hold a maximum of 2 electrons, and that's it. Now, when we're doing our Bohr models, we had those rules like 2, 8, 8, and so on. So the reason for that is the first energy level only has one orbital. Now, the outer energy levels contain 4 orbitals. Now, that's going to get a little more complex the more you study more chemistry, basically at the university level, but for now, we're just going to stick with, we start with one. The first energy level has one orbital, then the outers have 4 orbitals. And each orbital can only take 2 electrons, so they can take a maximum of 8 electrons. So that's how we kind of got our rules. Now, orbitals can be empty, they contain 1 electron, or they can contain 2. And remember, electrons always fill empty orbitals first. Now, just kind of give you an idea on our first energy level, so it has 1 orbital. You can kind of imagine it looking like that. Now, all the other orbitals, or the energy levels, will kind of look like this around an atom, where we have 1, 2, 3, 4 orbitals. Each orbital can take 1, 2, 3, 4, 5, 6, 7, 8. Right? So that's why we have those definitions of a 2, 8, 8 rule when we go up through our Bohr models. So this is kind of a more typical example where they're not all full. So if we have unpaired electrons, we call these bonding. So this is a single valence electrons in an orbital that can be shared or transferred with another atom. And the thing is, it needs to be single. If they're paired up, it's not going to happen, because when they pair up, we have a lone pair, or what we call a non-bonding pair. And this is 2 electrons occupying the same orbital. Obviously, if they're not in an orbital, there's no electrons, so we're not going to call it anything. So if we look at our little diagram right here, we can tell we have our lone pair, or our non-bonding electrons, because we have 2 electrons in this orbital at the top, and we have 1, 2, 3 bonding electrons in other orbitals. So it's only when you have a single electron in an orbital can it participate in bonding. So that is why when we look at just kind of make things nice and neat, if we have an empty orbital, that means there's 0 electrons. Half filled, we have 1, and if it's filled, it's going to have 2. How we describe these are half filled, these are unpaired, and they are ready for bonding. Whereas if it's filled, these are paired up, and they will be non-bonding. So that's kind of the description of what they are. Now we're going to break up into Lewis diagrams, Lewis diagrams we will, but we need to look at Bohr models for one more time, and this will be the last time ever looking at Bohr models, because we use Lewis models. So we've already looked at Bohr models when we did our Science 10 review. So just remember, I'm going to draw them here for the sodium atom and the chlorine atom. So remember, in order to draw a Bohr model, first we need to figure out the atomic number, or how many protons are in the nucleus. So for sodium, atomic number is 11, therefore there are 11 protons in the nucleus. So I'm going to start with, in the middle, right, protons equals 11. And we have our nucleus. Now I'm going to draw the energy levels around. So I'm just going to use a different color. So our energy levels, for sodium, same thing, we're going to go back. So sodium, we can't really see, so this is row 1, row 2. Sodium is in row 3. So that's the third row on the periodic table right here. That means sodium is going to have 3 energy levels. So we go 1, 2, and 3. Now because sodium has 11 protons as an atom, it's also going to have 11 electrons. So when we start putting them in, the first energy level could only take 2, 1, 2. The second can take 8, 1, 2, 3, 4, 5, 6, 7, 8. And finally, there's only 1 in the outer to make 11, right? So that's one way you can count. 2 and 8 is 10, 11 right here. Or, what should we have before you look at the group number here? It's in 1A, therefore it has 1 electron in the valence. We'll revisit this later. And then, of course, the chlorine atom, very similar. So when you look on your periodic table, you find chlorine, which is over here. Right, chlorine is in position 17, meaning that it's going to have 17 protons. So P positive equals 17, and we complete the nucleus. Now the energy level, chlorine is also in the third row on the periodic table. So that means it's going to have 1, 2, 3 energy levels. And same thing, because it's an atom, it needs to be electrically neutral. So if we have 7 protons, we need 7 electrons. 17 protons, we need 17 electrons. So first energy level can only get 2. Second energy level is also going to be full. It can take 8. And 2 and 8 is 10, so we need 7 more. So 1, 2, 3, 4, 5, 6, and 7. All right, so that is what we've been using so far to model our atom configuration. Now, as you can tell, these take a while to do. So we are going to propose a new model that's going to simplify things but still get the important aspects apart. And if you just kind of read back, the whole thing about Lewis only cared about the valence electrons. So that means for like the sodium atom, Lewis didn't care about these 10 electrons filled here. He only cared about this valence electron right here. And same thing with chlorine, he would only care about the valence electrons around here. So what we have is, the purpose is, we're going to determine how many bonding electrons are present, and therefore how many bonds can form. So we are going to, first of all, when we're writing Lewis structures, first we're going to write the symbol of the element it represents. So we're not going to write this like P positive equals 11 or P positive equals 17. If we're dealing with sodium, we write the chemical formula, Na. If we're dealing with chlorine, write the chemical formula, Cl. Now when we write this on paper, it's going to represent the nucleus plus all of the electrons except the valence electrons. So that means that when we write the symbol, we're assuming that we have the correct number of protons, correct number of neutrons, and all the filled energy levels. Now the valence electrons are shown as dots around the central symbol. Now we're not just going to toss in dots all willy-nilly, we need to actually have some set of rules here, all right, because we have the orbitals we have to take into account. So we have some rules. First of all, write the element symbol to represent the nucleus and the filled energy levels. Basically, write the element symbol. Next, we determine the number of valence electrons. And once we figure out how many, we need to add dots to represent each electron. Now, remember, once we get past energy level 1, so we get into 2, 3, 4, all the other energy levels that we're going to be dealing with from our things, they have 4 orbitals. So each of the 4 orbitals are represented by the sides of the element symbol. All right, so imagine that if we write an element symbol like Na, right, we have four sides. One side, two side, three side, four sides. And these are going to represent our orbitals, the sides on our chemical symbol. And we're going to place one electron per orbital. If additional locations are needed, after the orbitals are half full, we add a second electron until a maximum of 8 electrons are reached. Now, hydrogen and helium are the only examples because they only have 2. That's it. So, an easy way to determine how many valence electrons there are, look at only the A groups will help for this. So, for example, lithium is group 1A, right? 1, so it has 1 valence electron. Chlorine is, I know it's group 17, but look below the 17, it's group 7A, so it has 7 valence electrons, right? So that means you have to look not here, but here. What number is attached to the A? It's not going to work for the B's, so do not try to do it for the B elements, all right? That's a completely different thing. So let's look at lithium. Lithium, chemical symbol is Li. Now, we still need to draw our Lewis dots. Lewis dots around this, but before I start that, I need to figure out how many valence electrons lithium has. So I go to periodic table right here. I find lithium, which is right here, lithium. Now, we will notice lithium is in group 1A, meaning that it has 1 valence electrons. So, in order to represent this, I need to draw 1 dot on any side of this lithium symbol. So I'm just going to choose here, and that is it. That is the Lewis symbol for lithium. Let's look at boron. Boron, chemical symbol is B. Let's go to our periodic table and find boron. So we'll notice boron is over here. Sorry, let's get some of that thing off. So boron is right here. Now boron is in group 3A, indicating that it is going to have 3 electrons. So when we're putting them in, we have to fill empty orbitals first. So you can start anywhere with boron. If I want to go here, right, start here, that's 1. So that's one side. I have to go to another side, 2, and another side, 3. I cannot pair them up. I need to fill empty orbitals first. So that would be the Lewis symbol for boron. Let's try nitrogen. Symbol is N. Let's find nitrogen on our periodic table, which is right here. So nitrogen is in group 5A, right? Remember, V is 5. So it has 5 electrons. Now when I start filling in my symbols, right, I'm going to choose one side. 1, 2, 3, 4. Okay, so I filled all my orbitals. So all my orbitals are half filled, and I still need one more electron. So now I start pairing, and I can pair up my last one anywhere. So I can just pair it here if I want to. Boom. So we have paired electrons. So this is my lone pair. We got 1, 2, 3 bonding electrons here. All right, and the last two, oxygen is O. Periodic table, oxygen is right here. It's in group 6A, indicating it's going to have 6 electrons. And how we put them in, we go 1, 2, 3, 4. It's all full. Now let's start pairing. 5, 6. So we got 2 paired, 2 unpaired. And finally, the last one, argon. You're going to notice argon is all the way over here. Right here, it is in group 8A, indicating that it's going to have 8 electrons, which we go 1, 2, 3, 4, 5, 6, 7, and 8. So all the electrons are paired up. So with that, keep that in mind. See if you can complete the practice for yourself right here. Now, with these here, I'll put the answers up in a few seconds. I'll give you a warning, but just make sure to try these on your own first. All right, so we have sodium, calcium, aluminum, carbon, chlorine, neon, phosphorus, and that is it. All right, so pause the video. The answers are going to go up in 3 seconds. All right, and these are the answers. So this is hopefully what you have gotten. Now there's going to be one more thing we're going to touch up on before we finish this section, and this goes into assignment that has been posted up on Google Classroom, and you've probably seen it posted up there as well. So it talks about electronegativity. And this is going to be kind of the thing that anchors this entire unit, is the idea of electronegativity. So when we look at what it is, electronegativity just describes the relative ability of an atom to attract a pair of bonding electrons into its valence or level or its valence orbital, or it's just the ability to attract bonding electrons. Now, electronegativity values are based on the following 3 points. So one of them, these all refer to this right here, distance from the nucleus, and this specifically means the bonding electron. So the further away is from the nucleus, the weaker the attraction. Shielding by inner electrons. So what this means that if you go back to our Bohr models on our previous page, now notice how I pointed out here, this is the valence electron, all right? So this is one electron in the valence. This is the only electron that sodium can actually bond, either give up or share with. It will give up because it's a metal. But that means all these electrons inside, so these field energy levels, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 electrons shielding the nucleus. I probably just spelled nucleus wrong. Either way, NU. Yeah, I did. There's no E in that. That's NU. And that just crashed. Wait, hold on one sec. Let me get that back up. Okay, perfect. Got it working again. These 10 electrons on the inside here, we're going to call these shielding electrons because they're kind of blocking the nucleus from the valence or the bonding electrons. And last but not least, the number of protons will also affect electronegativity. So of course, the more protons, the greater the attraction. Now, these are just some trends as well that you'll notice when it comes down to like atomic size. You'll notice that, the smaller the atom, obviously there's less protons, less neutrons, less electrons, so they're much smaller, right? But you will notice as you go across, so from left to right, they tend to shrink. When you go down, they tend to get bigger. So going from left to right, obviously if they're shrinking, we're increasing the number of protons and we're decreasing the distance from the nucleus. So we have two things that affects electronegativity positively. And then of course the number of shielding electrons across here stays the same. But as we go down, right, we're increasing the size, increasing the shielding electrons. So something to think about. Now this whole electronegativity scale was developed by Pauling. He based the scale on the most reactive element, gave it a 4.0, and the non-reactive one gave it a 0.8. Don't know why these numbers were chosen, but I should probably look that up at some point. So metals tend to have low electronegativities, and they lose electrons, and non-metals tend to have high electronegativity, so they tend to gain or attract electrons. So we're going to get into it more obviously with the assignment, but when we ask anything about electronegativities, we're referring to these things only affected. Now you're probably wondering, where do I find the electronegativities? Well, you're going to find those on your periodic table. So if you look at your periodic table, the number right below the atomic number, that's your electronegativity, right? So lithium has electronegativity of 1.0. Beryllium has electronegativity of 1.6. Boron is 2.0, and so on. So you should be able to see those on your periodic table, and that is the electronegativity. Cool. So that is our first lesson for this one done. We'll go back tomorrow. We'll look at forming ionic bonds. All right. See you guys later.